Welcome students in the online organic chemistry lecture series. Today in this video we are going to study about this point, that is Friedel Craft alkylation reaction. As the name itself indicates, this reaction has been discovered by these two scientists, that is Friedel and Craft, in the year 1877. Okay, so in this year these reactions were discovered. So actually two reactions, that is Friedel Craft alkylation and Friedel Craft acylation, was discovered by this Friedel and Craft. What is this Friedel Craft alkylation that we will study in this video, in this particular video? So first of all, the Friedel Craft alkylation means the introduction of alkyl group on aromatic ring. Okay, so that is known as Friedel Craft alkylation reaction. Very simple. Just to introduce the alkyl group on the aromatic ring, that reaction is known as Friedel Craft alkylation reaction. So I will take a general reaction. Say for example, I will take a benzene. Okay, and if we treat this benzene with alkyl halide, I can say, say for example, I will take alkyl halide as a CH3Cl, and we will require the Lewis acid. Say for example, I will take here AlCl3. So in presence of this methyl chloride and Lewis acid AlCl3, this benzene is get converted into the toluene. Okay, so this CS3 group is introduced over this benzene ring. So this reaction is known as Friedel Craft alkylation reaction. Okay, so what are the reagents required for this reaction? Remember, the reagents required for this reaction are alkyl halide. Okay, alkyl halide. Along with alkyl halide, we will require a Lewis acid. So here I have taken the alkyl halide as a CS3Cl, that is methyl chloride, and Lewis acid is here aluminum chloride. So in presence of alkyl halide and Lewis acid, the aromatic ring system is alkylated, I can say. So this reaction is known as Friedel Craft alkylation reaction. Now we will see the mechanism of this reaction. I have written this reaction once again here to explain the mechanism. So in mechanism, we will see first of all, the first step in the mechanism is the generation of electrophile for this reaction. So generation of electrophile, how electrophile is formed to react with benzene, that we will see first. So this methyl chloride will be reacted with this AlCl3. This is, it is Lewis acid. So what is the speciality of Lewis acid? Lewis acid can accept the electrons. Okay, so electron from this chlorine will be attracted towards this aluminium. So there is a development of delta positive charge over this carbon, and here delta negative charge over this aluminium. So in this way there is a formation of such a ion complex here. Now the benzene which is in the surrounding to this complex will attack over this in this way. Benzene is electron rich species because it has 3 pi bonds, that means 6 electrons are there inside the ring. So benzene is electron rich species, so this benzene attacks on this electron deficient carbon and this chlorine goes away. So there is a formation of this intermediate, I can say. So these two bonds will be as it is. So there is a formation of this CH3. Here is a hydrogen, and here there will be positive charge. Now this intermediate is resonance stabilized. As you know the mechanism of electrophilic aromatic substitution reaction. So this bond will shift over here, and here is development of new positive charge. So these two bonds as it is. So here is a CH3 group, here is a hydrogen. Again this bond will shift over here, and there is a formation of new positive center in this way. These are the two bonds. Here is development of positive charge here now of CS3H. So these are the three resonating structures we can obtain for this intermediate, and due to this resonating forms, the intermediate is resonance stabilized. Now the next step in this mechanism is just the loss of this proton. So you can take any one of these three intermediates here. So I will take here the one of the these three intermediates. Say I will take the third one. Okay. So here is a CS3, here is a hydrogen, and here is a positive charge. So in surrounding there is a AlCl4 is there in the surrounding. So this AlCl4 will act as a base. So it will abstract this proton and this bond will shift over here, and there is a formation of our product, that is toluene, in this way. Okay. So this is our product. So in this way we can explain the mechanism of this Friedel Craft alkylation reaction. The first step is generation of electrophile. So this AlCl3 Lewis acid helps to generate the electrophile. So it will increase the positive character of this carbon. So that's why the benzene will easily attack on this carbon. So the intermediate which is generated, that intermediate is resonance stabilized by these three structures, and the last step is just the abstraction of the proton to form the product. Now here this is the complete mechanism of this Friedel Craft alkylation reaction. Now there are some drawbacks of this Friedel Craft alkylation reaction. That drawbacks we will see now. The first drawback of this Friedel Craft alkylation is the reaction does not stop at monosubstituted product. Reaction does not stop at monosubstituted product. Say for example, if I take a benzene, okay, if this benzene is treated with suppose a CS3 Cl in presence of Lewis acid like AlCl3, then we get the product, that is toluene. Okay. Now the problem here is that this, if we compare benzene and toluene, this toluene is more reactive as compared to this benzene. Okay. Why? Because CS3 is electron donating group. Okay. And due to this electron donation, the benzene ring is activated. So that's why this product becomes more reactive as compared to the benzene. So again, if we react this toluene with CS3 Cl and in presence of Lewis acid AlCl3, there is a formation of product. So here is a CS3. So it is electron donating group. So at ortho position or para position, there is a again alkylation reaction. So in this way, the reaction does not stop at this level, because the product which is obtained here is more reactive as compared to the starting material. So this is one of the drawback of this Friedel Craft alkylation reaction. Then another drawback of this Friedel Craft alkylation reaction is that electron withdrawing groups deactivates the ring. Say for example, if I take a nitrobenzene as a starting material, and if we do the this Friedel Craft alkylation, then the reaction is very slow, because this NO2 group is electron withdrawing group, and it deactivates this benzene ring. So the product is we get in a very slow matter. Okay. So this is the two drawbacks. One is reaction does not stop at monosubstituted level, and another one is electron withdrawing groups deactivates the ring. Another drawback is there. That drawback we will see. The third important drawback of this Friedel Craft alkylation is possibility of rearrangement. I will take one example and will explain this drawback. Suppose we have a benzene, and if you take the alkyl halide as a CH3 CH2 Cl, okay, and if we take a Lewis acid, suppose FeCl3, so what is the product expected here? the expected product over here is this CH2, CH2, CH3. So this is the expected product, okay? But actually this product does not form. Instead of that, we get this product. I will draw here the product. Okay. So instead of this product, we get this is the actual product which is formed. So this is one of the drawback. There is a rearrangement occurs. Now how this product is obtained, that I will explain. See, suppose CS3, CH2, CH2, Cl is there. So in the vicinity there is a Lewis acid Fe, Cl3. So there is a donation of electron from this chlorine to Fe. So there is a development of partial positive charge over here. Now there is a formation of this carbocation CS3, CH2, CH2 plus, okay, Fe, Cl4. But this carbocation is very unstable because it is a primary carbocation, we know. So there is a hydride shift, okay. Now how hydride is shifted, I will explain here. CS3, CH, H, CH2 plus, okay. So this hydrogen is shifted over here. So I will say here 1, 2 hydride shift. 1, 2 hydride shift. So hydride is shifted and there is a development of this carbocation CH, CH3 plus. So this is the actual carbocation or electrophile which is generated here, and then benzene will attack over this electrophile and there is a formation of this product. So I will write here the reaction. Suppose this is the benzene. So this benzene attacks over this secondary carbocation which is generated. Okay, so in this way it forms the intermediate like this, okay. And you know, in surrounding there is a Fe, Cl4, so it will abstract this proton and this bond is shifted over here and there is a formation of this product. Okay, so this is the actual product which is formed in this Friedel Craft alkylation. So this is all about the drawbacks or restrictions of this Friedel Craft alkylation reaction. So in summary, I will explain that Friedel Craft alkylation reaction is just the introduction of alkyl group on the aromatic ring system. So the reagents used for this reaction is alkyl halide in presence of Lewis acid. Okay, the mechanism is electrophilic aromatic substitution reaction mechanism, and we get the benzene ring alkylated. But the main drawback of this procedure is that the reaction does not stop at first product level, because the product which is obtained here is more reactive as compared to the starting material. So again reaction occurs to form another product. This is one of the drawback. Then second drawback was, if electron withdrawing groups are there on the benzene ring, then the rate of reaction is very slow. And the third drawback is a possibility of rearrangement. So such kind of 1, 2 hydride shifts are occurred and we get a different product rather than expected product. So this is all about the Friedel Craft alkylation reaction. So in this video we'll stop here and we'll meet in the next video with Friedel Craft acylation reactions. Okay, so we'll stop here. Have a nice day. Thank you.